survey. You guys have done that part. So we're going to assign the introduction part for your IA. I'll put an assignment here in my Notre Dame later today about this. But if you look in the IA place, it tells you the description of how to submit things, what you're looking at, what I'm looking for in your introduction. So again, you need your name correctly formatted, for the way you want to save your file, right? You need a cover page with your candidate code. You need some kind of explanation about why you thought this was an interesting topic and what kind of motivated you to choose what you chose. A statement kind of discussing what it is you're planning to do. You know, like, I'm going to write a survey and collect some data from my peers to analyze, yada, yada, yada. Clearly identifying what you believe to be the independent and dependent variable in your particular experiment. And then like a detailed plan. So like how you're going to go about doing this, the statistics that you're going to use, what those statistics are going to measure. Stop talking, please. You don't need to include any actual numbers in this. But part of your detailed plan is, okay, we're going to collect the survey data and then analyze it. These are the statistical analyses we're going to do and what we hope to get from them. Okay? If you need help on that, we can certainly talk about it more, but I just want to kind of plug this today. Let's try to have this like Tuesday next week. Is that reasonable? Basically a week to kind of grind out a paragraph. It'll probably end up being like a page, but you know. Everybody's cool with that? I'll get that onto my Notre Dame later today. But we should be able to do that. Okay. To do the scatter plot and correlation piece, you may need some of the stuff we're going to be talking about in chapter 14, just as a heads up, but we'll get through that by Friday, I think. Let's ready to rock and roll. Let's do the darn thing. All right. In section 14.1, we're going to be talking about scatter diagrams. When we talk about a scatter diagram or a scatter plot, what are we really talking about? Just a bunch of data points plotted, right? And just like plotting X's and Y's. That's all we mean. So keep that in mind the whole time in 14.1 here, what we're talking about, really all we're talking about is plotting points. So the big idea throughout all of chapter 14 is going to be this idea of correlation. So this has a specific statistical definition as opposed to the English language correlation. Statistical correlation has a specific definition as opposed to the English language word correlation. So when you have bivariate data, that is data that consists of two measurements taken from every individual in your sample, just like you're doing in your survey, you can calculate a correlation that is the relationship between the two variables. Note that when we use the term correlation, We don't imply a specific type of relationship, whether that be linear or quadratic or exponential or whatever. We say two variables can be strongly correlated or weakly correlated, but in both cases are still considered to be correlated to one another. In addition, correlation just means that there is a relationship, not what the relationship actually is. Therefore, you would need additional information to determine the nature of that relationship. Everybody's okay? So when we try to determine a type of correlation, or determine the level of correlation, you first have to decide what variable is going to act as an independent variable and which variable should act as a dependent variable. So the independent variable is the variable controlled by the experimenter. It's the variable that is hypothesized to be the cause of some effect on the other variable. So for example, Megan, I think you were looking at the number of cars in a household and then the number of trips to Costco in a week or something. So your hypothesis would be that having more cars is going to cause you to take more trips because potentially that's more gas you'd be buying at a cheaper rate. So that the number of cars would be the independent variable, and then your trips would be the dependent variable. So that the dependent variable is the response variable. It's the one that's being affected by the independent variable. Everybody's okay with that? I think some of us looked at, like, Isaac was looking at like running speed and number of stolen bases for MLB players. The idea that the faster you're running, the more bases you should be able to steal. So if you're talking about like height and hand size, what would you say there?
Height is the independent.
I would agree. Typically, as individuals grow, the bigger they are proportionally, all their parts are bigger, right? Hands, feet, head, arms, legs, the whole shebang, right? What about the money spent on advertising and the amount of product the company sells? Good. Yeah, we would suspect that the more you advertise, the more stuff you can sell. Absolutely. Now, is there like a specific mathematics that we're doing here to decide independent, dependent variables? No. What are we using? Kind of common sense, right? So it's just you have to think about it and apply some common sense, but it's typically, if you think about it for a minute, like which one should cause the other, it's usually pretty clear. So one way to show the relationship between these two quantitative variables is to construct what's called a scatter plot. So the values of one variable are going to appear on the horizontal axis and the values of the other variable on the vertical. And each individual then appears as a single data point on the graph. So you need to decide which one goes on each axis. The explanatory or independent variable should go on the x-axis. Explanatory for x-axis. Probably we've talked about this already in your previous math classes, right? Trig and pre-calc kids, we talked about doing like regression stuff last year. You may have remembered that. You need to then label and scale your axes. So label means like, for Megan's it would be number of cars, and then the y-axis would be like trips to Costco. And the scale would be like each tick mark would be like potentially 1 unit, right? Like 1 car, 2 car, 3 car, 4 car, etc. And then like 1 trip, 2 trip, 3 trip, 4 trip. Now, if you're doing something different, like if you're Isaac and you're looking at running speed, on your x-axis, that's something that's probably measured to the 100th or 1000th. I can't remember when you showed me the statistic, how fine of a grain they were measuring that. But there you may want to consider going like 10th of seconds or something. And then the number of stolen bases, I would probably not go by ones, but probably 5s or 10s, because some people steal, 50, 60, 100 bases in a season is not, was very uncommon for a while. I think somebody stole a bunch of bases this year. But that's always, you have to think about like what your data set looks like to pick a decent scale. And then you just plot the individual data values once you've done that. So basically you're just plotting points, right? All right. So to describe a scatter plot, like what it looks like, we're looking at kind of 3 things. So again, we want to describe the overall pattern and any striking departures from the pattern. Essentially, what we're looking for is the direction, the form, and the strength of the relationship. Those are the 3 things that we'd want to get from looking at our scatter plot, looking at our data points. And then also worth discussing is possible outliers. So when we talk about direction, that's what we're talking about, is whether the data points appear to be like increasing or decreasing, right? So whether there's like a positive overall slope or a negative overall slope. The form refers to the shape. Does it look like the data points in a straight line? Do they look like they're in an exponential curve? Do they look like they're like a quadratic curve where it's making a parabola? Does it do something crazy like look like a circle? I don't know what kind of experiment you would have done that you got like your data points that look like a circle, but it's possible, I guess. And then strength talks about is really about a measurement of how close your data points fit to the shape or the form that you're talking about. So if your data points look really close to a straight line, you might say that that's strong correlation. If it looks kind of like a line, but it's not very tight, you might say it's like moderately strong. If it's just kind of like crazy, you might say it's weak. Just, we're not using anything more than like some vague descriptors here. And then outliers we've talked about before, right? So when we talk about direction, we're talking about whether the 2 variables have positive or negative association. So this one right here would have negative, because if you look, it appears to be going down as you move from left to right. Everybody agree with that? What is the shape or the form of this? What do you guys think?
What do you mean by that?
So like what type of function, the graph of what type of function appears to resemble this? You might say linear. I think there's probably a better answer because it seems to flatten off here at the end. I might say exponential, because this kind of looks like it's curving and then kind of flattening out. That's kind of what exponential curves look like. But linear wouldn't be bonkers. That's not like a crazy choice. I just think there would be a better one. You'd get a stronger fit on an exponential would be my suspicion, but sometimes it's tough to tell just by looking. We'll do it numerically later. And then the strength of this, would we say this is how close to a straight line does this look? Yeah, moderately close, right? Like you can tell the shape is there, but it's not like the most obvious thing in the world. It's kind of a thick band, but that thick band has an obvious shape to it. I'd say that's moderately strong. So we might say there's a moderately strong negative curved relationship or exponential between the percent of students in the state who take the SAT and the mean SAT math score. Further, there are two distinct clusters of states and two possible outliers that fall outside the overall pattern. What would you say the two possible outliers? This one here, and then I would bet this one here also seems to be like out of the band, right? And we see that there's like, kind of one cluster here, and then like one cluster up here, and there's not a lot in the middle. It's pretty sparse there. So that's kind of what our description sounds like. Is everybody okay with that as a description? Again, have we done any math yet? Not really, right? We're just kind of talking about what we see with our eyes and using some vocabulary. Okay. Oh, there they are. So the strength, we said moderately strong. The direction, we said was negative. And the form, we say curved or exponential. So again, that's us working that description into a sentence that's like, rather than just like listing, which is a little bit more elegant, rather than just like a list of things. So let's take another example here. What do we see here? Okay. Certainly seems that the direction is positive. I agree. The form? I agree. I think linear this time. That seems to be pretty straight as an arrow. And then the strength of it? Moderately strong. Yeah, I agree. Are there any outliers, do you see? I don't think so, right? I think that everything will work out if we ran the 1.5 IQR test on these. I think all the points would work. So in general, it seems to be that teams that score more points per game have more wins. That's probably not surprising. And the teams that score fewer points per game tend to have fewer wins. So that's a positive association between points per game and wins. There seems to be a linear pattern, right? Looks like there's a straight line to follow the graph. And the strength, we would say, is fairly strong or moderately strong because it looks like a line, but it's not super tight. And we said that there are no outliers because it seems like everything is pretty much kind of in that same straight band. We feel good? Okay. So what we want to do eventually is to take our scatter plot and create a mathematical model that we can use to approximate, okay, if we had this much of, this independent variable value, what would we expect the dependent variable to be? So basically, if we have this input, what do we expect to have as an output? The way we do that is with something called a line of best fit. So the line of best fit is basically a line drawn on your scatter plot that gives the best representation of correlation between the two variables. You can estimate it from just looking at your scatter plot. You can just draw on a line that's kind of as close as possible to all the points. We'll talk about how to do this mathematically, or one way to do this mathematically. There's like actually a lot of different ways to do it mathematically in a little bit. However, when we're just doing this, the one thing that we need to have happen is that our line of best fit should pass through the mean point. What do we mean by mean point? Well, it's just a point that's the mean of the x coordinates and the mean of the y coordinates. Everybody's okay with that? Its name is exactly what it is, right? How do we do a mean? Add up the number of values and divide by the number of values, right? Like, so again, we find that mean point, and then when we draw our line of best fit should go through that mean point, but you still want it to be as close as possible to all the other points, like overall. Like the overall distance between your mean line and any of the points is minimized. That's kind of what you're looking to do. Now that's a very mathematical description, but all right. The last thing I want to talk about is the difference between correlation and causation. So a causal relationship is one in which one variable is determined to be the cause of another variable's change. That's extremely difficult to prove from either an experimental standpoint or mathematical standpoint. Correlation is a much weaker condition. For example, I have this stapler here, right? Sits on my desk every day. Not one day I've ever seen a tiger in my classroom. So this stapler must be causing like a tiger repelling field that's somehow keeping all the tigers away from us, right? I'll sell you this tiger repelling stapler for $10,000. You'll never see a tiger as long as you have this stapler with you. What do you say? That's a causal relationship, right? Do you buy that causal relationship?
No.
Definitely not. Like, that's ridiculous, Mr. Kulik. Is there a correlative relationship between the presence of the stapler and the presence of tigers?
Yes.
Yeah. Is the stapler causing that relationship?
No.
No. So we have to be really careful when we're using our vocabulary. The difference between causation and correlation is very, very different, right? Very different standard. You can claim all kinds of crazy things if you're going to substitute causation for correlation. In all likelihood, what's really keeping the tigers away? It's the fact we live in Michigan and there's no tigers in Michigan outside of a zoo or like some crazy person in the, living in Detroit that has a tiger in their house somehow.
Baseball.
The baseball team, sure. Those aren't actually physically tigers, but I get your point. It was a clever joke. I appreciate it. So in general, proving a causal relationship, we don't even really try in mathematics. That's something that you're left to really what industry is really interested in a causal relationship between two things?
Science.
Pharmaceutical in particular, though, right?
Yeah.
Like, you got to know that the medication is what's actually causing, the person to get well, and it's not like a placebo effect. Like you have to really, it's a very expensive, takes a lot of time and effort to try to design an experiment to prove that your medication is actually doing what you claim it's doing. It's why the pharmaceuticals are so expensive is because that process is like potentially billions of dollars of investment to get that drug from, the laboratory to the market. So again, we just kind of gave an example of two variables that are strongly correlated, stapler and tigers, but no causal relationship, right? So one of the reasons why correlation may not be related to causation is the presence of like a lurking or confounding variable. So the example of our stapler and tiger, the variable that's really causing the relationship is our geographic location, right? The fact that we're in Michigan. Now had tigers roaming around free in Michigan. Now, if we did the same thing in, like rural India or something where there are tigers like running around in the wild still, may not find quite as strong of a correlative relationship, right? That your geographic location is a much bigger factor there. That's really the variable that's probably causing the relationship. Or I would propose would be the variable. Or if you handed Diego this stapler and then dropped him in the tiger pen in the Detroit Zoo, probably not going to have any good things happening there, right? All right. So again, another example, we might observe that 100% of NDP students get accepted to colleges. So you might say that, attending NDP causes a student to get accepted into at least one college, right? Doesn't seem like that's the exact causal relationship. How many of you assume that you would be going to college even if you go to high school here? Probably all of you, right? Why? Because you probably come from a family of means where that's an expectation. Like you're academically talented enough to get accepted in here. So you've already like pre-selected the student body to be students that are very capable of doing of getting accepted to a college, all those sorts of things, right? Lots of possible reasons that are unrelated to actually attending school here, but attending high school in general and being, a talented and ambitious student. Okay, that was it for this first section. Let's go and look at some of the in-class examples here. All right, I'm going to call on some random students. So let's pull up my random student generator. So I wrote some code. It was like last year or something. I think I did this. But to do like a bunch of random classroom tasks for me. You just do it. You just start fooling around trying to do stuff and then do a lot of Googling. No one taught me anything. I figured it all out myself. Okay, that looks fine. Random student, our first is going to be Luke.
Are you serious?
I am. It says so right there. All right. For the following situations, identify which is the independent and which is the dependent variable. Comment on whether you believe the variables would be strongly or weakly correlated and why. The ACT score of a student and the amount of sleep per night the student gets on average.
So the amount of sleep per night would be dependent.
So you think that if you get a good ACT score, you're going to sleep more?
Oh, the ACT score is, so ACT score is the dependent variable.
Okay.
The amount of hours per sleep is the independent variable.
Okay.
It's strongly correlated.
Okay. I might not go strongly, but I would say there's like moderate correlation there, because the kid that gets 20 hours of sleep and doesn't go to high school probably isn't going to do very good on the ACT, right? Like, so think about that kind of, and like, is it going to, for sure, more is always going to be better?
No.
No, right? Like at some point, if you like sleep through the school day, you're probably not going to do
There's
real
like a
good.
cutoff.
Yeah. But in general, like a well-rested, healthy student should do better than somebody that's like a non-sleeping wreck, you know. All right. Let's see. Who's next? Let's do that again. Random student. Here we go. Gavin. The number of hours spent exercising per week and the number of years a person lives. The years the person lives is the dependent, so the exercise is the independent. Okay. What kind of level of correlation do you think? Positive. Okay, sure. And then do you think strong or weak? Pretty strong. Is it like infinitely strong? No, why not?
I mean, that's all you do. Don't eat. Forget about it.
Okay. Or how about even better? Accidents happen, right? Like healthy people that are like exercise and like eat well and do all the right things still die young because car accident, or, you know, they drown in a pool, or, you know, like life happens and sometimes, you know, they get shot in a drive-by shooting or something,
That's not good.
right? Are there factors to living a long time that are more important than amount of exercise?
My nutrition.
Probably nutrition and diet. I would say also like geographic location. Like, are you living in an area where you have access to good affordable medical care, as opposed to, you know, are you living in a hut in Central Africa or something where you have like access to the stuff in the jungle or whatever?
Yeah.
You know, like there's lots of things I think are more important for a long life than exercise, but I certainly think there's probably some positive correlation there. I don't think it's going to be the strongest thing ever.
Yeah.
Because like you look at like a professional bodybuilder, I don't expect those men to be living like super long lives, even though they're spending a lot of time doing that, because there's a lot of other unhealthy factors that go into that particular pursuit. Or if you look at the average lifespan of an NFL player is like shockingly low. And certainly they spend a lot of time every week exercising. So yeah, so this is what when I talk about like the why of like trying to decide like how strong or weak or whatever the correlation there is. Those are the kind of things to think try to think through. And again, what am I using to do that? Just like common sense and real world experience and stuff, right? All right, who's next? Let's see. Random student. Katie, who's absent. Oh, man.
It's not long.
Matt, you are next. The distance you live from a body of water and the amount of snow you receive in your backyard every year.
Yeah, I didn't hear you say it again.
Yeah, the distance you live from a body of water and the amount of snow you receive in your backyard every year. Which one is the independent? Which one would be the dependent variable?
The dependent is the snow.
Mm-hmm.
The independent is the distance.
Great. And would you say that relationship is like strong or weak?
Weak.
Weak. Very good. What's your example of why it's weak?
I feel like that makes a difference.
Okay. So can you name a place where you'd live really close to a body of water and not expect to get very much snow?
Beach.
If you lived like in Florida, right? Yeah. If you live in a tropical location, you can live right next to the water, and you're not getting in no snow, right? What was I trying to trick you with here? Lake effect snow in Michigan was that I was trying to trick you with, but you saw through it. So that was good. You need to, yeah, you sound like you're struggling right now.
I'm struggling.
Yeah, life's hard. All right, I think we got one more question here. Christian, you're going to be up. Let me go scroll down here. All right, so determine the direction, form, and strength of correlation for each of the following scatter diagrams. Just do A here, Christian.
Alright. The direction, is that one that's like negative or positive?
Correct.
So, that looks like it's negative.
Agreed. The form,
let's say linear.
I would agree. That's your best choice, I think. And the strength,
It's moderately weak.
I'd say moderate to weak. Yeah. So it's, I would say moderately strong to bordering on weak, I think is fair. Everybody agree? Like there's kind of a line shape to that, but that's a pretty wide spread of points to be considering it linear. So that's good. B's going to be next, and our person answering B will be Aiden. So B right here. So we're looking for direction, form, and strength.
It's negative.
Okay. Maybe. The form is like the shape.
Linear.
Okay. The correlation, B.
That's not linear.
So when I look at this, what does this look like to you guys? Looks like nothing, right? So I would say that like there is like no direction, no form, and like no correlation, you know, because it just looks like a random mess of nothing. Everybody's okay with that? So like we didn't talk about that as an example. You drew a hard one there because but your instinct that you're probably thinking was like, this doesn't look like anything. I'm just like, do I have to say something? Because I don't really want to say anything,
Yeah, I could see linear.
right? Well, if you actually did the calculations, that would probably be your best fit, would be some kind of linear relationship. But the correlation's going to be lousy. All right, and then C's the next one here, and that's going to be Isaac.
Got the size of it.
C, what do we got here?
Positive, and then linear.
Yeah, good, I agree. Yeah. The last one says, for the following set of data, plot a scatter plot diagram, then draw a sketch for the line of best fit, and make sure to include the mean point. So let's do that here. So I'm going to use the computer to help me out here a little bit. Which one should be the independent? Which one should be the dependent? This is height and shoe size. Yeah, and shoe size should be dependent, I agree. So height's going to go as my x coordinates. Oh my goodness.
You have a phone set?
While let's see, we need to set our graph paper. So height, we're gonna go say from, stop throwing stuff, you goobers. 50 to 80, and then like, I don't know, 0 to 15. So there's our stuff, and then we need to calculate the mean point, right? If we're going to draw the line of best fit. So let's do that real quick. So I already typed these into lists L1 and L2 on my calculator. So I'm just going to do a 2-variable stat on that because it'll give me both the x mean, which is 70, and the y mean, which is 10. So here is my scatter plot. This guy right here is my mean point. So if I'm going to draw my line of best fit, so it looks like I have 4 above my line and then 4 below. That looks okay. You know, so maybe something like that. That's not quite through that mean point, though. Let's do a little better there. You know, so maybe something like that. What do you guys think? Art skills matter. Yeah, so like neatness counts here. Some of us, that's going to be a bigger problem than others.
It's just an estimate, right?
It is an estimate, yep. We're going to learn how to do a best fit line mathematically here later on, but that's the gist of it right now. I'm going to start 3.2 as well, given the time. We probably won't do the in-class examples for section 2, but we should start it. Especially if I'm asking you to write something about it later on, right? So here we're going to be talking about measuring correlation. We talked about kind of what correlation is, and we just kind of like used our eyeballs to vaguely describe correlation as like strong or weak or moderately strong or whatever. So here we're going to kind of look at this mathematically. So linear relationships are going to be one of the most common relationships we study. It's an easy relationship to identify. If you look at a data set, it's easy to pick out a linear relationship. It's also a fairly common one that we see. Very oftentimes, like a little bit in makes it like a little makes a little different, all right, let's say a little makes things a little bit better and a lot makes things a lot better. Everybody's okay with that notion? So that's oftentimes the case with a linear relationship. So the PMCC stands for Pearson's Product Moment Correlation Coefficient. We abbreviate that as the letter R. And that measures the direction and strength of the linear relationship between two quantitative variables. Stop talking, please. So some facts about this statistic. R is always between the numbers -1 and +1. Positive R's indicate a positive correlation. Negative R's indicate a negative association. If your R is near 0, that indicates a very weak linear relationship. You can't, like an R value of actually 0 is kind of just a theoretical possibility. Would imply you have like infinitely many randomly distributed data points, which in practice you're never going to see. But if you have R values that are like, less than 0.5, that's usually pretty good evidence that there's not a lot going on there. The strength of the linear relationship increases as R moves away from 0 towards -1 and +1. The values of -1 and +1 occur only in the case of a perfect linear relationship. What do you mean? What do we mean when we say perfect linear relationship? It means that every single point in your data set is a point on one specific line. So if you draw one line or you write your best fit line, every single data point is going to lie on your best fit line. That's what you're saying. Everybody's okay with that? All right. Yes. So to interpret what some of these R values mean. So if we have an R value that's between 0 and 0.25, and we're looking at absolute values of R, right? So between 0 and or -0.25 and 0, the same thing holds. But those are very weak. Between 1/4 and 1/2, weak. Between 1/2 and 3/4, moderately strong. Between 3/4 and 1, we're going to call very strong. This is just our criteria. If you're doing this in industry, the industry probably has their own separate criteria for what they're considering, strong, weak, moderate, etc. Some things are, like real life is actually pretty noisy, and to get R values like this are almost unheard of if you're doing like a real life thing where there's lots of variables kind of in play. All right, so let's look at some numerical examples. If you saw something like this would be like correlation 0. If I look at this appears to be kind of like some negative slant to it. If I look, it's kind of like I have a big, fat, thick, straight line, which would indicate it's pretty weak because that's a pretty thick, straight line. I have to use a pretty thick marker to like draw my best fit line to kind of absorb all those points. Here, I see things going up positively, and it's a little bit thinner, right? Especially kind of through here. We have a little bit more data. It's still pretty bad because we have this stuff here and here is pretty widely spread out, so it's not like you got much improvement. Visually, with your eyes, can you tell the difference between 0.3 and 0.5? Probably not, right? This would be something you'd do numerically. But I sure as heck can tell the difference between a 0.7 and a 0.3, right? This looks much more tightly packed into a line shape. Even more so with the 0.9. But again, for me, I'm not sure I could tell the difference with my eyes, difference between a 0.9 and a 0.7. But I sure as heck can tell a 0.99. where that looks like a line, like a pretty liney line, right? So this is just to give you an idea of like visually what these different levels of correlation look like. And to a great extent, it's pretty tough to tell the difference between like, you know, some of these, right? You know what I'm saying? So again, we're going to, for each graph, estimate the correlation and then state the direction, form, and strength. Let's take a look at this one. What do we see here? Dots. What is the direction? Positive, linear, and the strength? I would say that's pretty darn strong. What kind of R value would you approximate this at? I would say 0.9 and above. If you said anything in there, I would say is probably good. Okay. B, what do we see here? I'd say it's positive, right? As we move from right to left, things are basically moving up. The R value about 0.4. I'd say that's fair. You know, 0.3, 0.4, 0.5, any kind of thing in there I would take. R value of 0, I think, is a reasonable estimate to this. It appears that there's no relationship at all, right? Everybody okay there? Again, we're just kind of estimating. We're doing no calculation here. We're just kind of saying, okay, you showed me a bunch of pictures of kind of what it looks like to be these things. Here's some more pictures. How about this one? I think it is negative also. I would say this is pretty weak negative. If you were like 0.3 or below, I think that's pretty or negative 0.3 or below. I guess it would be above for negatives. God, that's confusing. But like here, I have, like points here are lower than the points over here, but sort of the points over here, there doesn't seem like there's any kind of like negative or positive lean to it. But if I look over here, definitely seems like there's some downward, especially if you kind of like skip some of these outliers over here and over here. If you just kind of look at the middle piece, that looks pretty negative. Does you guys buy that? No? Yeah, it's hard. All right, let's talk some more about correlation. So when we do the calculation for R, there is no distinction about which variable you call independent, which one you call dependent. It doesn't matter. So whether I flip I flip the coordinates and graph them the other way, I'm going to get the same R value regardless. If I change the unit of measurement for X or Y, your value for R will not change. If I convert, if I'm doing height versus shoe size and I change all the heights from like feet, like 5.32 feet, to like some number of inches, the correlation should stay the same if I do that for every data point, right? Everybody's okay with that idea? That value of R has no unit of measurement, it's just a number. So it's not like feet per inches or something, depending on your independent, dependent variables, it has no unit at all. So one thing we have to be careful about is to do this, we have to have quantitative variables. What's quantitative mean again? Yeah, it's measured numerically, right? So like if we were asking favorite color, grade level and favorite color, you couldn't do an R value calculation on that because the color part is not quantitative. The R value is not going to describe curved relationships between variables, no matter how strong that might be. So if you have something that looks like a perfect parabola and you calculate the R value for it, it's going to say that the correlation is pretty weak. Even though you can look at it and be like, oh, that's a great fit for just a different shape. So this is only works for linear relationships, this R-value calculation. And we say that R is not resistant because it's strongly affected by just a few or maybe even a single outlier. So this could be very affected by outliers. So example, if I have like a straight line of dots here, and then I have one more like way down here in the corner, the correlation is going to be lousy, even though you can tell like, well, it's a perfect straight line. This one guy like way over here is going to screw everything up and give you a lousy correlation. That's what the third bullet point is saying. And then the last thing is we'd say this is not a complete summary of two variable data, because for the reasons we just discussed, like if you have outliers, it can wreck the correlation, that R-value calculation. If you have a nonlinear relationship, it's going to wreck that R-value relationship. So there are still things that like we don't get a good measurement if we look just at R. Everybody's okay? So how do we do this calculation? We'll show you how to do this in practice, but in general, we're going to use your calculator to find it. The only time you're probably ever going to write out the calculation-ish for how to do this is when you write your IA. But in practice, we're just going to do it on the calculator. So here is the formula. You're going to look at the product of the difference between your first data point and the mean for both x and for y, divided by the standard deviation for x and the standard deviation for y respectively. So you're going to look at the product, and you're going to do that for every single data point, and then you're going to add those up and divide by the number of data points. That's what this calculation is saying. So usually you write it with the summation, the sigma here, that just says the sum of the data point, x data point minus the mean of x's divided by the standard deviation of x's times the y data point minus the mean of y's divided by the standard deviation of y's. And we add that up for all the data points and divide by n. Right? That's all that calculation is saying. On your calculator, I guess we'll wait and do it when we do it on the in-class example. So these correlation and regression equations are going to be powerful tools. So if I have a bunch of data points here, I can calculate a line of best fit. That's going to give me a regression equation here. So the price is equal to some like y-intercept minus a slope times the miles driven, which is like my independent variable, like my x. And then I have this r squared value. We'll talk about what that means in the future here. Now, what happens if I had flipped the x and y axis? Right? Notice here the regression equation changes, but the r value, well, this is r squared, but it's related to the r value, remain the same, right? So you get a different regression equation depending on which is your independent and dependent variable, but your level of correlation does not change. So again, we remember that correlation and regression describe only linear relationships. So, want to see something crazy here? Guess what the R value is for each one of these? It is, yeah, it is the same. There it is. Is that bonkers or what? This is why R gives you an incomplete picture if you look at R alone, right? Are all three of these distributions the same? No. Are they even kind of alike? No. Would you use the same words to describe any of them other than maybe they have like some positive association, except for this last one with like, what the heck is going on with this last one? Right, that's weird. Okay. Oh, and in fact, they all have the same regression equation, which is even bonkers, right? That's some crazy stuff there, guys. All right. We mentioned that correlation and regression are not resistant, meaning that they're highly affected by outliers, the presence of outliers. So take a look at this graph here, the age of first words and the Gesell test score. I don't know what that is. It's some child development thing, I guess. It looks like we have two possible outliers, which I've called child 18 and 19. With all the children, our R value is negative 0.64. If I eliminate child 19, the R value changes to negative 0.76. And if we lose child 18, it now drops way bad to negative 0.33. Why did it improve when we lost child 19, but get worse when we lost child 18?
Child 19 is further from the regression lines.
Yeah, child 18 actually is not really an outlier in that it looks like it's fitting the trend of the other data. Child 19 definitely doesn't fit the trend of the overall data. So again, here the outlier helped your regression. Here the removal of this outlier hurts your regression. Not resistant, right? Those outliers are making a big difference. All right. So how do we actually calculate these regression lines, these best fit lines? One method involves what's called the least squares approach. So you're going to like you draw on your best fit line, and then basically you're going to draw a square that goes from the best fit line to the data point. And you're going to try to arrange that best fit line to minimize the area of the squares. So what you're going to notice is for outliers, the area in that square is going to be huge, and it has an outsized effect on the way you build that best fit line. So the takeaway here is those outliers in the x direction, like child 18 was, where it's following the overall pattern, but it's way far away from the other x's. Oftentimes that one's going to be okay. The ones that are in the y direction, though, the outliers in the y direction, those are the ones that are going to, removal of them should help your regression score, your R value. Because if I'm drawing like a box here, that's just a little box, right? If I'm drawing this box here, that's huge. You guys get what I'm saying? So another type of correlation is called Spearman's rank correlation coefficient. And this ignores the type of relationship between the variables and only measures if there's a consistent relationship, either increasing or decreasing between the variables. So we abbreviate that statistic with the symbol R with a subscript of S, or this Greek letter rho that kind of looks like a P. And this just measures the consistency between the relationship, or the consistency of the relationship between two variables. So just like R, this is always between -1 and +1. Positives indicate a positive direction and negatives indicate a negative direction. Near zero indicate a very weak relationship. We increase the strength of our relationship as we get closer to -1 or +1. And those extreme values of -1 and +1 occur only in that perfect rank order relationship. So let's look at some examples here. So we say that mobile phones often lose their resale value quickly after they are purchased. The following data is collected from one particular model. So the month since purchase, and then the percent change in value. Woof! 87% loss of value after 2 years. Here's the graph. Is this relationship appear to be linear? No, it looks kind of exponential, right? If we do the R value, the relationship is negative 0.74. So we have a strong negative linear relationship, despite the fact that this data doesn't really look linear. So I put that up here. Notice that's our R value. What if we look at the Spearman by doing a rank order? To do this is done by just numbering the data for each column in order from highest to lowest. For example, 24 months since purchase is the highest value, so it will change to a rank of 1. Conversely, 0 months since purchase is the lowest value, so it's going to change to have a rank of 13. Hi. Okay. Go ahead. That's her stuff right there. So again, we've just changed this to 13, 12, 11, 10, all the way down to 0. And we'll do the same in the second column. So our new rank order becomes this. So the biggest value gets 0. So 24 is our biggest number. That becomes 0. 0 is our biggest value. I'm sorry, 24 is our biggest value, becomes 1. 0 is our biggest value, it becomes 1. And then we just count from there. Everybody's okay? So we're ordering it from 1 is the biggest, and then we go down to the smallest, right? Everybody's okay? Now we regraph. If we look at that, woo, doggy, that looks pretty good, doesn't it? So if we do that, the R value should come out to be almost perfectly -1, negative 0.995. So all I did to find this number was do the correlation coefficient calculation using my rank order data set. So I did the same calculation as here, but my data set was this.
1 is the highest of 13, but then it just goes down to the lowest. So that's like
So Isaac, the highest x is 24, so that's 1. And the next highest x is 2, and then 3, 4, all the way down. The highest y is 0, because the other ones are negative. So that's 1, and then 2, 3, all the way down. Okay? So what we're finding here is that this data set has a near perfect negative order. This means that as the month since service or since purchase increases, the change in value decreases on a consistent basis. It's not telling us the shape of that consistent basis, but it'll tell you that it's consistent at least, right? What if we reversed them? What if we picked the smallest one as 1 and did the same thing? So we just do that. What do you suspect is going to happen? Oh! It's the exact same, right? We got the exact same graph. And the Spearman coefficient should be this exact same as well. Cool. What do I do if there's ties, right? If this is a rank order thing, what do I do if there's ties? So here's our data set. Notice that I have a tie here in my X's. And do I have another 6.5? Oh, there's another 6 point. So I have 2 ties in my X's. When I rank them, what am I going to do here? What did I do here? Oh, I see. So like these guys are both the same spot, so they're both getting the same rank. So 4 is the 9th. You know, this is 8. I didn't write them in order, which was kind of a dumb decision. 7 is the highest, that gets the 1. 6.5 is the next highest, so those both got 2s, or all 3 of them got 2s, excuse me. You guys see what I did? I didn't change the order of I didn't write it in order. I just gave them the rank orders. So again, all these ties, we just, you know, the thing to keep in mind though, is because I went from 1 and I did 2, 2, and 2, my next value is going to be 5 because that's the 5th thing that we've ranked. Everybody's okay with this? If you guys look at, well, let's think of a situation. Like if you look at track and field standings for like a field event where there's ties, like the high jump, happens all the time. If you have a 3-way tie for 2nd place, the next points are assigned to 5th place. That's how that works. That's a pretty specific example. I couldn't think of another example where that happens all the time. All right. So these guys, to find their rank to use with the Spearman's correlation, we just average their spots they occupy. So this is 2nd, 3rd, and 4th spots. So they should get 3s. These guys are 10th and 11th, so they should get 10.5s. So the true rank should be this. Did you see what we did there? So we resorted them and included the ties where they occurred, but that's not going to be accurate. So these guys don't all get 2s. They get the average value for places 2, 3, and 4, which is the same way you assign points in a track and field meet if you have ties for an event. The people that are tied at 2nd place all don't get 2nd place points. They get the average points for 2nd, 3rd, and 4th place. If you're not a track coach, you probably never encountered this in your life. This is the best example I can come up with. So now that we've done that, we're ready to do the rank coefficient. If I do the correlation coefficient calculation for this data set, my Spearman value is 0.814. If I did the wrong ranks, notice my Spearman value is worse, right? So it's really important that you do that adjustment at the end. And let's stop here, guys. I think I still had a bit more here, but this feels like a good place to end because you guys are starting to get antsy.